presenting VirtualLab Fusion 2021.1. So, from the title, you will already have surmised that today we're going to talk about the latest release, the latest version of the fast physical optics modeling and design software, VirtualLab Fusion. The approach that we're going to take is the following. We have selected a few of the most prominent new features of this version, and we are going to showcase them. We're going to illustrate their potential along a series of examples, and we're going to group these examples on the basis of fields of application. So we have mostly 3 blocks of content that we're going to be looking at: fibers, then crystals and anisotropic media, and finally microlens arrays. This approach, however, is going to leave some features, some new features, some of the changes that have been implemented in this version are going to be left out. So we cannot cover everything. We're not going to go exhaustively through the list of everything that has changed, everything that is new in this version. And so that's where I'd like to start. In case you're interested in seeing that exhaustive list of changes, in case you're interested in reading everything that is new in this 2021.1 version, I want to tell you how you can find that detailed information. So that's the first stop of this webinar. And the first place where you can find that information is in the follow-up material of the webinar that you will receive from us 1 or 2 days after participating in the webinar. And this is a very same presentation that I'm going to be using as a conducting thread for the webinar today. And on the very first slide after the title slide, you will find a series of bullet points with links of interest. The Lightrons website, our social media presence is there too, a repository of examples and use cases, which is a great place to find great information about VirtualLab Fusion and different examples of the potential of the software at large, not just this version, but in general, the potential of VirtualLab Fusion can be greatly illustrated by diving into that downloads section of our website. In this case, in this webinar, we have added a new entry to that list of links of interest, and that is a part of our website devoted precisely to this new version 2021.1. You can see it there on your screens right now. So in case you would like to see all that information, that includes the release notes of this version, but also a collection of use cases devoted precisely to illustrating the potential of this new version in particular. Everything is there. So I encourage you to take a look, pop around that part of our website in case you find a new feature that we will maybe not have time to discuss here, but that will be of particular interest to you. That's the first place where you can find that information about the release, that detailed information about the release. But for completeness, I also want to show you how you can find that very place, that part of our website yourself. So simply go to lightrons.com. That would be the Lightrons website. And then under Products and Services, VirtualLab Fusion Release 2021.1. There, that will take you to exactly the same place as that previous link. So there you have it. Again, I encourage you to take a look, see if you find something interesting there. And with that, we can conclude this introduction and move on to the examples, to the 3 main blocks of content that we're going to be discussing today. The first of these blocks is fibers. And inside this block, the first example that we're going to be taking a look at, that we're going to be playing around with, is an investigation of the effect of aberrations on the focal region of linearly-polarized LP fiber modes. The setup that we're going to be working with is this one. We start with a step index fiber as our source. Then you will see in the documentation, in the presentation, as well as in this particular use case, that later on in the use case we repeat the same experiment with a graded index fiber, but we start with a step index fiber here. And we can read on the slide all the defining characteristics, all the specifications of this fiber, the wavelength, the core diameter as well as the two refractive indices that we need to construct this fibre in particular, the refractive index of a core and the refractive index of the cladding. Then the light emanating from this source meets the first lens, which collimates the beam, and then we superimpose a certain aberration phase on this beam. The way we do that is with an idealized element, a functional element, where we simply define which aberrations and with what strength we want to use, and then they are simply on the plane where that component is located. Those aberrations are superimposed onto the beam that reaches that component. Then the beam, this time including those aberrations, propagates on to meet the second lens here, which focuses it onto the focal plane. And of course, the presence of those aberrations will impart a certain deformation to that focal spot. That is precisely what we want to investigate here. That's what we want to see, how that focal spot is deformed by the presence of these aberrations. Now, the experiment or the simulation starts by determining which modes propagate in our fibre. And to do that, we use the fibre mode calculator. That is the first new feature that we want to showcase, that we want to mention in the field of optical systems containing fibres. And this feature allows us to configure a specific fibre, both step index and graded index, and to obtain the modes that are propagating in it. So we're going to take a look at what this looks like, how this works in VirtualLab Fusion itself. We can already see the user interface for that calculator, for that fibre modes calculator on screen right now, but let's move on to VirtualLab Fusion to get a bit of a look and feel of how things work there. So here we are, this is VirtualLab Fusion 2021.1, and I have already prepared the files corresponding to this example. Among them, the first thing that we have discussed so far, the calculator, which you can see right now. And we're not going to go in detail through everything, we don't have a lot of time, but it's fairly easy to see that we have here the parameters of our fibre. We can select the mode type depending on whether we have a step index or a graded index fibre. We started with step index, so we select Bessel modes, and we see then that we have 6 propagating modes in our fibre, and we can read the characteristics of those modes here on the table on this right hand side: azimuthal order, radial order, propagation constant, and effective refractive index. This same information can be read in a bit more of a graphic form by clicking here on Show Mode Structure, and this is precisely the same information from this table. This graph can be a bit hard to read at first perhaps, but it contains exactly the same information here. We have as the abscissa the index of the fibre. We have 6 modes, so we would have points at 1, 2, 3, 4, 5 and 6, and then the different graphs show the information pertaining to the different columns that we have here: azimuthal order, radial order, effective refractive index, and propagation constant. The propagation constant uses the ordinate axis on the right hand side, all the other 3 the ordinate axis on the left hand side. So if we wanted to read, for instance, I'm going to move the legend because it's blocking part of the information, and I can do so via the property browser, legend alignment, and here I can select a new position. Let's do top center. That gives us a clear view of everything. So if I wanted to read the propagation constant for the first mode that we, for the mode with index 1 that we're propagating, that is propagating in this fibre, I would go here to 1 and then find the red curve and read the value from this this ordinate on the right hand side. Then if I wanted to see the value of, say, the radial order for this very same mode, I would find the triangle, the graph, the line with the triangle pointing upwards. That gives us a radial order, and it would be this one, so it's index 1. That's the way we would read the information from this graph, and so on and so forth. So that is a different way of providing this same information. And then finally we can actually look at the modes. So we can create the fields, the fields that represent the different modes here. So I click on that button and we get a document containing our 6 modes, as we can see here at the top. We get information about the order as well, and we can go through them, see what shape they have. So these are the 6 modes that are propagating in our fibre. That is the first step of this example. Let's return to the presentation to see what else is in store. Now we know, because of this fibre mode calculator, which modes are propagating in our fibre, which modes are being delivered by our fibre source. So then we need to create the system with a source that generates this mode sequence, and then these modes which are generated by the source will propagate further in the system, as we have already described. And then, so this is what we already know, this is what we just saw. These are the modes that are generated by our source. We saw them with the fibre mode calculator. And then after propagating through the system, look at the arrow, how it indicates at which point in the system we are looking, or we're placing our detector. Then we can also see the result at the focal region, including that aberration phase and how what deformation that aberration phase imparts on that focal spot per mode, per fibre mode. But of course, the final result is a combination of all those modes. So we're also interested in seeing the coherent combination of all these modes that are being generated by our fibre. So at the top there we have that combination at the exit of the fibre, that would be the input plane of our system, and then at the bottom we have the final result, what the focal spot would look like, including all the modes that are being generated by that fibre, and with those superimposed aberrations on top. So all these results are generated with VirtualLab Fusion. Let's maybe take a brief look at how things go there. Here we are again. We have everything as we just left it a minute ago. I'm going to close this document containing the mode fields, and I'm going to minimize the calculator, and then we're going to look at the system. And sorry, that's the one for the grin fibre. Let's look at the one for the step index fibre, which is what we have been looking at in the slides. So we have 2 different sources here in our system. A fibre source, this will allow us to work with a single mode each time. And the multiple light source, let's double click on it, allows us to combine different individual sources, which in effect means we can include all those 6 modes that we know are being generated by a source in a single source. So we have here all those modes that we just investigated implemented in the multiple light source. The multiple light source is incidentally also a new feature of this latest version, and the fibre source as well. So the fibre source individually, as well as a mode of combining the different modes together inside the multiple light source, are both new features of this version. So Then we have all the rest of the system. We have our fiber end here. This is a surface that separates the fiber from the embedding medium, and then we have placed a detector here to look at the fiber modes as they leave the fiber. Then we have our first lens, this component that superimposes the aberration phase. Let's double click on that. Take a look at which aberrations we're actually using. So here under physical parameters, we're using the Zernike fringe type aberrations, and we can see what coefficients we're actually using here. So we have astigmatism in X and Y with different strength. We also have coma in Y, and that seems to be what we're using, the aberrations that have been defined here. So that is the way in which we define those aberrations that we want to superimpose on our beam. Then our second lens, and finally a detector at the focal position. So I can run the simulation with just this single fiber source. Remember, this just generates a single mode. In this case, the one with azimuthal order 1 and radial order 2. Let's take a look at that simulation with field tracing. And we're going to get two results, one for the fiber end and one for the position of the focus. So this is the fiber end, this is a mode after leaving the fiber, and this is a mode at the focal position, including the effect of those aberrations. I'm going to minimize these results, and I'm going to change the source that I'm using to include all the different modes that are generated by the fiber. And I run the simulation again, and this time we're going to get the full result, not just one mode, but the result including all of them, both for the fiber modes after leaving the fiber at the input plane of our system and at the focal position. Here, that detector that we have called diffraction pattern. And all 6 modes are being propagated and combined in a coherent way to produce the final result. And here we have it. Again, 2 results, 1 per detector. Here, the modes after leaving the fiber, and here that look at the focus, including the effect of the aberrations. That would conclude this part of the example. Then, as I said, we repeat the same procedure for a graded index fiber. We can maybe take a look at the results quickly, but we're not going to repeat the experiment in VirtualLab Fusion because the flow of things would be very similar. So we once again have an investigation of the modes that are generated by the fiber and their pattern, the diffraction pattern, including the aberrations at the focal region in the focal plane, and the combination, the coherent combination of both situations for the overall result. The second example in this content block devoted to fibers in optical systems will be an investigation of the effect of atmospheric turbulence on fiber coupling into a few mode fiber. The context for this example is free space optical communications. And once again, we use a scientific publication as our reference. The citation is, as before, at the bottom left corner of the page here. And let's investigate this sketch that describes the system that we're going to be simulating. So we start with a fundamental Gaussian beam as our input field. That takes us to the top right corner of the sketch. So that's where we start, input field Gaussian. And then we collimate that beam using a lens, as is shown here. And then the effect of that atmospheric turbulence, or that air turbulence, is going to be simulated by using a phase-only SLM for different values of the strength, so to speak, of that atmospheric turbulence. And as we can read on the slide, d over r0, that parameter, is a typical way of evaluating the strength, the magnitude of that atmospheric turbulence. And we try with different values of that characteristic parameter. So by reflecting our input, a collimated input beam, on that SLM that is going to simulate the presence of atmospheric turbulence, we then propagate on towards a beam splitter that is going to allow us to look at the scattered field after the atmospheric turbulence, and another part of that beam, beam that has already interacted with the air turbulence, will propagate on towards the second lens that will focus it onto the entrance of a few mode fiber. And then we can also investigate the output after the fiber, which has a length of 500 millimeters. Some additional parameters of a problem are also shown on this slide. Now, the new feature that we would highlight with this example, or that we want to highlight with this example, is the fiber coupling detector for multimode fibers. We previously had a fiber coupling efficiency detector for single mode. Now we have this new added version that we use in this example. We can use 3D ray tracing to take a look at our system before performing the analysis to check that everything has been positioned correctly. And so that's what we can see on this slide. And then we perform the analysis, this simulation, for different situations: a single mode fiber, a 2-mode fiber, and a 4-mode fiber. So we can see the different blocks here for those 3 situations. Again, we use the mode calculator. We would use a mode calculator at this stage to determine the modes. And on this next slide, we investigate the results of that simulation. We can see and going downwards on this panel of results, these results are generated with VirtualLab Fusion 2021.1. Moving downwards, what we have is an increase in the strength of the atmospheric turbulence. Then the leftmost column corresponds to, as indicated by the arrows on the page, corresponds to the scattered field by the air turbulence. Then the second column corresponds to the entrance of the fiber. So this is what reaches that input position, that entrance position to the fiber after being focused by the lens. The scale of the result is indicated at the bottom row. And then as we move to the 3rd to 6th columns, we find the results after the light has propagated through the fiber, the 500 millimeters of the fiber. The loop in the fiber that is shown in the sketch is just to indicate the fiber, but it's not part of the physical system. The fiber would have a straight structure, would be in a straight line. And then, as I said, 3rd to 3rd, 4th and 5th. Sorry, I said 6th before. 3rd, 4th and 5th columns correspond to the results after propagation also through the fiber, and superimposed on for the different fibers that were investigated: single mode, 2-mode and 4-mode. And superimposed on those results, we can read the values of the coupling efficiency, which have been calculated with that new detector. Once again, the same experiment is repeated with a graded index fiber. The analysis would be analogous to what we have just done, so I'm going to skip it for the time being. If you're interested, again, you will receive all the documentation of the webinar so you can take a look at it yourselves. With that, we conclude the first block of content on fibers, as we have seen lots of exciting new features there, and move on to the next block, crystals and anisotropic media. And the first example that we're going to look at here is Birefringence. So we very simply have a linearly polarized Gaussian wave, which is going to propagate through a uniaxial crystal, a calcite crystal. And we're going to orientate the optic axis of this crystal with respect to the direction of propagation of the beam and its polarization, so that the birefringence effect inside the uniaxial crystal will separate two different polarization states inside the crystal. And so we'll get two replicas or two modes, two beams out of that initial single beam after it has propagated inside the crystal. So let's go directly to VirtualLab Fusion for this example. Here we are again. The system, as we can see, is rather straightforward from the point of view of the number of components that we have. We have our Gaussian wave source, we have our calcite block, and we have a detector to observe the field, the light, after it leaves this crystal block. So initially, our light is polarized along X. It's linearly polarized along the X-axis of the global reference, the global coordinate system of the setup. Now, this is, of course, we have a lot of possible references here. The crystal itself is going to provide, it's going to impose a given coordinate system on the problem. So we start from this polarization state that we define in the source refers to the coordinate system of the source itself. Then let's take a look at our calcite block. So we are using a crystal plate component. This is one of the new features and which implements the new technology, the new solver for anisotropic media. We have the possibility of using that new solver inside the crystal plate component or as a layer in coatings. Also, we're going to see an example about that later on, but in a coating it can be in combination with isotropic media as well. So it can be one layer of many, that anisotropic medium. But here we have simply a crystal plate component, and we can define the medium that we're using in this type of calcite crystal, and we can of course define the orientation. And this is what this is also referred to that global coordinate system provided by the source. So we set here the theta and phi angles of the crystal of this anisotropic medium. We can observe, we can see graphically represented the qualities of this anisotropic medium by clicking here on this view button, and we're going to see the ellipsoid, the index ellipsoid corresponding to this crystal, and this gives you different, you can enter a given direction here that will help you visualize how things are set in the problem, in the system itself. So this new feature, this new solver for crystals and anisotropic media comes also with this added visualization tool specific to such media or media with such properties. So we have set it up in this way, so that the beam impinges at an angle with respect to the optic axis, and we can generate that birefringence effect. Note this phi at 45 degrees. Remember that the initial polarization was linearly polarized at 0 degrees. And so we click OK here. And then finally we have a detector that is going to allow us to visualize a field as well as a polarization state, the polarization ellipses at this plane. And you can see the small angle icon here in the positioning controls of this detector. If I go to orientation parameters, we can see this rotation angle around Z, also of 45 degrees. This means that we are going to rotate the detector in its plane, so we're not going to change the detector plane, but we're going to rotate around that main propagation direction that is Z in order to place or to locate the two replicas of the beam, the two beams that will be generated by or split by that birefringence effect along the horizontal of our detector. We can take a look later at what happens if we do not use this 45-degree control here in the detector. And so, without any more talk, I'm just going to run the simulation of the system with field tracing, and we can see here the two replicas, or the two sub-beams, the two modes into which our original beam has been split by that birefringence effect of a calcite crystal. If I zoom in, we can observe the polarization state of each of these replicas, each of these modes, one along the horizontal axis, one along the vertical. Note that we have rotated the detector 45 degrees, and that will influence the definition of a polarization at this plane exclusively. Let me illustrate that by simply removing here this 45-degree angle and setting it to 0. That means we, of course, do not use that rotation, and run the simulation again. We're still going to get the same physical result, but now at 45 degrees. And again, the inclination of those polarization ellipses, which in this case are lines at orthogonal polarization states, linearly polarized, are also have a different inclination because of that rotation of the detector. So this lets us see or visualize what the effect of that rotation in the detector plane is. Evidently, we're changing the coordinate system of that detector exclusively. And we could, of course, perform parameter variations here in this system, the thickness of the crystal, and we can see all those results in the example. Let me open the files, the corresponding files, although we also have the results on the slides. So here we have a parameter run. This allows us to vary parameters in the system and observe their effect on the different detectors which have been included. And what we change here, we could select any system parameter to change, but what we are actually doing here is change the thickness of our calcite block. And the simulations have been run already. Let's advance, let's move on, and we can create an animation out of this sequence of results. We can see here in the top row the values of the thickness of our calcite block and the corresponding results. Again, the simulations have already been run in advance. If I double click here, this will create the corresponding animation of this result, and we can see how the separation of the two outgoing beams changes as the thickness of the crystal increases, and we can see that effect in video form, in an animated form. Another interesting effect which we can investigate with this new anisotropic solver in VirtualLab Fusion is the following polarization conversion in uniaxial crystals. When anisotropic media are introduced in optics education generally, one of the first notions that one encounters is that if we're talking about a collimated beam, about a plane wave, and that plane wave propagates parallel to the optic axis of the crystal, which means that its polarization state is going to lie in one way or another in the normal plane to that optic axis, then because all those polarization states are equivalent with respect to the reference provided by the crystal, then no tangible effect will appear. However, that assumes that we're working with a plane wave and that we can consider that the polarization vector, that the field is going to vibrate in one way or another, but that we can assume it's going to be contained in that normal plane to the optic axis. In this experiment that we're going to perform for this example, that we have performed for this example, we focus light onto the crystal. And it is true that the main propagation direction is along the optic axis, but because we no longer have an ideal plane wave or a beam which can in any way be assumed to be collimated, and therefore that focusing effect is going to cause that assumption that the polarization vector, the field vector, is going to lie in the normal plane to the optic axis. That is no longer true. It can no longer be true. And because of this, interesting effects will appear in this experiment. Once again, we use a scientific publication as a reference. Experimental measurements from that publication on the left of this slide. On the right, we have the results generated with VirtualLab Fusion. So this solver works for collimated beams for ideal plane waves, but also, as it's demonstrated here, it works just as well because of the general framework that is used and the very comprehensive framework that is used. It works just as well for focused light as in this example, and we can observe how the interesting effects that appear, those vortex, those phase dislocations that are caused by the propagation through the crystal, are also reflected in the simulation result of this example. This example showcases the use of anisotropic media as one layer among many, alongside isotropic media as well, in a coating. This means we can, in VirtualLab Fusion, make any combination of isotropic and anisotropic layers in a coating, and that is the feature that is used in this example. Again, we take a scientific publication as a reference for this simulation experiment. The background here, the technical application background, is an LCD display, and the additional polarization handling and play that we can perform with the inclusion of anisotropic media in this stack, in this layer stack, means we can, or the authors of the initial paper demonstrated, that it is possible with that strategy to recycle more backlight for an LCD in the construction of an LCD. And that is as I said, the background, the technical background, the application background of this experiment. And in that publication, as we do in this use case with the use of VirtualLab Fusion, they investigate the different parameters that go into the functionality of the device. And just as one example here, one of the results that are demonstrated or investigated in that initial paper and that we replicate with simulations in VirtualLab Fusion is how the number of layers will influence the efficiency of the device across, in this case, the abscissa represents the wavelength of the radiation, and of course we want to cover as broad a range as possible. later on, the premise of the paper, of the initial paper, goes they combine not just one multi-layer setup as is investigated here, but they combine several with different thicknesses and different configurations in order to cover a broader spectrum. So there are additional conclusions and additional studies in that initial publication. And it is clearly visible here how with 20 layers, the Bragg reflection condition is not fulfilled yet. We don't even reach 80% efficiency. And then we can see in addition the results for 50 layers and 100 layers. And according to the conclusions of a paper, taking into consideration also fabrication constraints, in this case for the purposes of that paper, the 50 layer situation would be enough here. And just let's close this with a brief look into VirtualLab Fusion, how those layers, isotropic and anisotropic, can be combined in a single coating, as we discussed. Here we are again. We have a very simple setup, very straightforward setup with a plane wave source, a stratified media component, and an efficiency detector. And in this stratified media component is where we have that multi-layer stack. In this case, this is just for one stack, and then, as I said, additional stacks are combined to increase the wavelength range in which the device is going to function. So that would be, as I said, an additional premise or an additional conclusion of the paper. But let's just, from the point of view of being interested in the new features of VirtualLab Fusion 2021.1, let's take a look at that coating, how that coating is defined, and in that combination of isotropic and anisotropic media. And that's what we have right now on screen. We start with a uniaxial crystal layer. We can manipulate the orientation, of course, that is fundamental when we talk about anisotropy, and then the next layer would be isotropic, then the orientation does not matter, so we cannot enter that parameter, we cannot manipulate that parameter. Then crystal again, isotropic again, and so on and so forth. And this takes us to the last block of content for the day, microlens arrays. We start with one of the most widespread applications of such components, such devices, Shack-Hartman sensors. And the objective, the goal of these sensors, of these devices, is to measure the wavefront of the incoming beam. Of course, in simulation, that's one of the good things about simulations, that we can actually look at the phase of a field in a simulation directly. We have that information, we have the field information. But in reality, we always need indirect measurement techniques in order to be able to see or to somehow measure the phase of an electromagnetic field, the phase of the light. And one of those contraptions, one of the ways in which we can perform that measurement is using a Shack-Hartman sensor. A sketch of the system would be this one. We impinge with a certain beam, in this case it's collimated, and each part of this beam is going to interact with one pair, ideally, of microlenses, and is going to be focused. So here, if we imagine this setup, this sketch functioning, each situation here is more or less equivalent. If we ignore potential diffraction effects from the sides of the initial beam, everything is the same. We have an on-axis plane wave which encounters the lens and is focused onto the final target plane. Then we're going to have a replication of exactly the same result. All the points are going to be equivalent. However, when the situation changes and the beam has a spherical wavefront, things are going to change, and each part, it can be, the whole situation can be thought of as if each microlens pair is going to see a slightly a part of the field that is going to have a different inclination by virtue of that spherical curvature of the wavefront. And so, depending on which microlens pair we're looking at, the corresponding focal spot will be more or less, will deviate more or less from its central position, depending on the inclination, the curvature of the beam, or rather the gradient of the wavefront at that position, rather than the curvature, the gradient. And finally, in this last example, we're going to simply look at the light propagating behind a microlens array at different positions, so directly behind the microlenses, then at the focal plane, and further on when the parts of the beam into which, the parts of the light into which the microlens has split the original beam, the original wave, because of the divergence of each of them, they overlap in space and generate additional patterns in the resulting light. So because we have fully coherent light here, so we're going to be able to look at that pattern that comes from the different beams corresponding to each of the microlenses interfering in the far field when all those beams overlap together. So that's what we're going to look at here, light propagating and behind the microlens, and we're going to look at what that light looks like at different stages behind the microlens array. So first we have here the field directly behind that microlens array, and we see that gridded pattern of all the modes. Then if we propagate a little bit, the apertures of each of the microlenses are going to create a certain diffraction effect, which can be observed. And I take this chance to mention another new feature, which is the modeling levels. If you have played with VirtualLab Fusion before with the previous versions, you will have surely encountered the different Fourier transforms that we offer. And a new feature, a new situation that we bring with version 2021.1 are these modeling levels, which provide default configurations of those Fourier transforms to make handling easier for those users who are not intimately familiar with the intricacies of all those Fourier transform algorithms. So it simplifies, it provides a bit of a roadmap, a bit of a guided tour, if you will, of how to progress through the simulation. And so with these modeling levels, we can switch off diffraction, as we can see on the right-hand side of this slide, or we can switch it on at different parts of the system. I will not go into depth. Again, I encourage you to look up the documentation about the release, about the version, but we can switch diffraction on, and that's what we have on the left here of those two results. So we can see what the diffraction caused by the aperture of each of those microlenses looks like, and we can switch off that diffraction if it were not of interest. Then we progress to the next stage, what the focal plane looks like, and we can see that spot here, only the central mode, or we can see all of them together. And then we can move on to the part where all the parts of the initial beam which have been split by the microlens array, where they all overlap and generate that additional pattern, that additional spot pattern. In this case, it's the interference caused by each of those parts of the beam that causes the spots. Initially, in the previous result, it was the focusing of each of the single microlenses at the focal plane of that microlens array. And at this situation, in the far field, where all the parts overlap, we can look at each of the individual results for a single microlens, or we can combine all of them together. Again, we're talking about coherent light, so they interfere and generate that spot pattern, which we can also zoom in and look at in a more detailed form. And perhaps the most revolutionary feature in this field of microlens arrays is the channel handling, which we're going to look at now in VirtualLab Fusion itself. So we have the setup here that corresponds to that experiment we have just seen on the slides. And I have gone to the channel configuration panel. And previously we already had channel handling in VirtualLab Fusion. For instance, what we call now master channels here in the microlens array component exist already and have existed for a while for all surfaces, all components. And this allows us to control in a non-sequential simulation the 4 different types of interaction that light can have with a surface. It can be transmitted through from the left, it can be reflected when it comes from the left, or it can be transmitted through from the right, or it can be reflected when it comes from the right. So this is what we control here in this first tab of master channels. But the new aspect, the new control, the new channel handling notion that is included with this new microlens array component is the subchannels in the X domain. And we have full control. We can select, currently we have 2 options. We can select none or structure related. Structure related means one channel, one subchannel in the X domain will be taken per microlens. And the option none will still have some internal channel handling, but according to the wavefront of the field. And both options have their uses. For instance, in the Shack-Hartman example, we used the option none. But when the edges of the different microlenses are important, when resolving that with or handling that with care is important, then it makes sense to use the structure-related X-domain channel decomposition. So this is also what allows us to look at the individualized results. We can observe what the light looks like just for one microlens, and we can select which one we want to look at, we want to analyze. We would do that here under channel mode management, and we can look at all channel modes or just a single one. So there are a lot of capabilities that are provided, that are suddenly facilitated by these new features, and in this context particularly by this microlens array component and the new concept of channel handling. That takes us to the end of this presentation of this webinar. I hope you found all the features that we have presented here today as exciting as we do, and that you're looking forward to working with them if you haven't already. And right now I am available to answer your questions about this new version, about the release, and about any of the use cases that we have discussed. Thank you for listening.